Okay, so new video. So I've done a new Newton's cradle experiment, put up a new setup, but it's basically the same in the sense that after the first run, more and more energy is lost. Okay, the ball starts to wobble a lot more and the pattern is lost very quickly. And yeah, only the first run is good enough to do analysis. So let's take a look at the slow motion footage. All right, there we go. That's the footage that we're going to analyze. So we only need the incoming speed of the one mass, right? And that we need to measure, we need to calculate the velocity. And then after collision, they both move apart and then they fall back again. And then after that collision, then the heavy mass will stay stationary and the one mass will leave. And those are the two cases that we will analyze. Now I have only analyzed the first one that already required a lot of time. So for this video, I will only analyze the incoming mass one, and then after collision where they both move in opposite direction. Right, so I've noticed that when I put the camera further away, that the resolution tends to get better. The quality is a little bit better. We can see the edges of the steel balls pretty clearly. Now, the raft science has been complaining about the frame rates, that they absolutely suck. Let's take a look at the frame rates, frame per frame. I think it's about 30 frames per second. But in each frame, we can still see the edges of the ball pretty clearly. Not perfectly, of course, it's still a little bit vague, but it's clear enough for me. So now, to measure the displacements of the balls, instead of doing it horizontally, right? I drew the circle, right, that indicates the trajectory of the balls. This was also a complaint about from draft science, that I should measure the arc, the specific arc, all right, instead of horizontally using the ruler only, because yeah, there is a little bit difference, of course, between horizontal line and arc, but it's negligible. It's a small difference. Also, another complaint was that only a couple of frames has been used to measure the displacement, 1 or 2 frames. So I don't know, how many frames do you suggest that I should to measure the displacement? 5 frames, 10 frames? Well, I've used 10 frames, right? 10 frames for this video. So let me just show you. So here are the series of images. So we start off with the 2 balls being stationary, and we will start with the small mass. Also, yeah, the bigger mass is, they are the same masses again. The big mass is 3.36 times as heavy as the small mass. If you do not believe me, I have recorded myself weighing the masses, so I can put it up as well. So we start with the small mass, and this is approximately the center of mass, this cross line, this point here, this intersection. And then I drew the circle. All right, so this is the trajectory of the small mass. It will move like this, it will follow this line. And this is, yeah, at moment, this is timings at this particular point in time. The one mass is over here. All right, you can see it's pretty much in the middle, the center of the middle of the line is in the middle of the ball. So it's at the center of mass roughly, which indicates that this line is pretty much correct. it's the correct trajectory. And then let's see, after 10 frames, the ball is over here, the one mass. This is right before collision. So this is to measure the incoming speed, the displacement of the incoming speed. So over here, we take this place, this point in space and time, and then 10 frames later, it is over here at this location and at this moment in time. And this is just another random place in time, just to show you that this line, this curve, indicates the correct trajectory of mass 1, because this line is once again here in the middle of the ball, about at the center of mass, roughly. So this is a good circle. All right, so oh yeah, so this one was before collision, right before collision, and then after collision, again, this is 10 frames later. So we have right before collision at this moment in time, then 10 frames later, it reflects back, it's over here. Okay, right after collision. This is for the one mass, and then I did the same for the second mass ball. So I took the point of center of mass, then drew the circle. So it follows this line here. This is its trajectory of mass, of the heavy mass. And this is the moment in time right before collision. So here, and then after collision, 10 frames later, the heavy mass is over here. So now we have to measure the angles. I took this software to measure the angles. This is called AutoCAD, which is used by professional architects and designers. So this is mass 1. Yeah, so I drew a line from the center till the edge of this left side of the ball. Again, yeah, when we zoom in, the edges of the ball are a little bit vague, but we still can have a good indication of where the edge could be. And it's approximately over here. I think everybody can see this, right? That is, this is the left edge, and the other edge is approximately over here. Okay. Even if I'm 1 millimeter off, I don't think that will make a big difference. All right. So now we can measure this angle with arc. Let's see. This is 111 degrees from here till here, 111. And then 10 frames later, the ball is over here. Okay, and then we measure that angle. All right, like that. And it's 93. So now we have to subtract these degrees, 111 minus 93, which is 18 degrees. All right, 18 degrees. There we go. So this is the angle for the incoming speed, the displacement of the incoming mass, 18 degrees. And then, so this is right before collision. And then after collision, 10 frames later, the one mass is over here. Okay, so this was 93 degrees, and now the angle is 101, so it's 8 degrees. This is a reflection, right? So after collision, the angle is 8 degrees for the one mass. And for the two mass, so this is, now I drew a line to the right side of the ball, right? We can clearly see that the edge is around here. It's approximately over here. The angle is 83 degrees, and then 10 frames later, it's over here. After collision, 75. All right. So 83 minus 75 equals also 8 degrees. So after collision, the angle of the two mass is 8 degrees. And then to calculate the distance of the arc, the length of the arc, we have to times the radius. The radius times the angle. It's that simple. Radius times angle will give you the length of the arc. So what is the radius? Well, they are all the same. We can measure it. It's 242. And it will all be the same. They're all the same size. 242. Yeah, the decimal numbers are a little bit different, but it's always around 242. 242. So the radius is 242. Let's say it's 2.42 meters. So times the angle, 2.42 times 18 equals 4.356. Hold on. Check it out. Not correct. Times. No, 42.56. What did I wrote? Oh yeah, I put it like this. 4.356. I think I changed the decimal. And then 8 times, yeah, I think I did 18 times 0.242. Right. So let's take 0.242. Yeah, each time times 0.242. Then we get the length for the first arc, 4.356. After reflection, after collision, the length of the arc after reflection is 1.936. And now for the two mass, the length of the arc is 1.936 after reflection. And then we can calculate the velocities, distance over time. So I know here we can see the timings. So we need to do delta t, delta time divided by distance. And that will give us 13.2 meters per second for the incoming speed. After reflection, the velocity is 5.69 of mass 1. After collision, the velocity of mass 2 is 5.69 as well. They are the same speed. Time is over here. These are delta t's. They're always 0.33 seconds. Those are the 10 frames. So 10 frames equals 0.33 seconds. And then we can start to calculate the momentums. So momentum 1 equals mass times velocity. So 13.2 times 1 times itself. So for mass 2, we're just going to multiply times 3.36, which is, because the 3 mass is 3.36 times as heavy as the 1 mass. So we can just pick 1 for 1 mass, and then for the heavy mass, we can pick 3.36. All right, so after reflection, momentum is the same. So 5.69 kilograms meters per second. For the heavy mass, we have to do 5.69 times 3.36, which is 19.13 kilograms meters per second. So now we know the momenta. All right, so now we're going to compare the models again. Conventional science versus draft science model. Conventional science says, right, after reflection, they both go in opposite direction. So one has to be negative, one has to be positive, because direction matters. So then when we do plus 5.69, yeah, or plus 5 minus 19, I think it has to be plus 19 and then minus 5. I think I switched the signs. It has to be plus 19 plus minus 5.69, and that equals 13.43, right? And so the initial momentum was 13.2, and when we add these together and treat one side as a negative, one direction as a negative, we get a total momentum of 13.43, which is a gain of plus 1.74%. So this is going to be the error percentage. This is our error, only 1.74%. And then for draft science momentum, okay, we treat momentum always as a positive, no matter what direction it's going. It's always positive. We never subtract momentum. If we do that, then we get 24.82 total momentum, which means, well, yeah, and the initial momentum was only 30.2, which means we have an increase of plus 88% of momentum. So once again, all right, once again, it has been shown that when we apply a draft science model, that we get an insane increase in total momentum, all right? So there's so much more free energy, so much more free momentum. So I don't know how long are you going to play this game, draft science? Once again, it has been shown, it has been proven that your model, all right, if you apply the fact that if you always treat momentum as a positive value, if you're never going to subtract, then yes, you always are going to end up with an insane amount of extra momentum. Whereas when you treat one side, one direction as a negative momentum and you subtract momentums, then momentum is conserved. Okay, I'm saying that your momentum never, that your model never conserves momentum. Look at these error percentages. Once again, only 1.74% error for conventional science and 88% error for your model. So obviously, this experiment must be extremely badly done once. Again, it has to be absolute crap experiment, because it creates such an error percentage for your model. Wow. So what are you going to come up with now? What kind of excuses now? Again, bad frame rates. So the details will only become smaller and smaller. Right? All these flaws, all these little flaws. Do you really think that even if all these little flaws are solved, that suddenly this 88%, this 88 error percentage is going to decrease to 1.74, and then for conventional science, the error percentage will rise, will increase to 88%, that somehow these error percentages will swap, they will flip, and it will come out perfectly your way. Do you really believe that? Come on. How many more experiments do you need? All right, that's it. And yeah, so this is only the first half of the video that I've analyzed. I will also do the second half of the video. But that's enough of a video for today. I think the point has been made clear again. Your model does not conserve momentum. You are the free energy nut. Your model creates the free energy, not the conventional science model. Energy is conserved because we treat it as a negative value. We subtract the momentum when they go in opposite direction. Yeah, well, as long as you do not accept that, then you are the free energy nut.